Okay, it is 2 p.m. now. So I think we can get started. Hello everyone. Welcome to the second session of the Introduction to Logic course. Our speaker for today is Dr. Patrick Lutz. He is the Hedrick Assistant Adjunct Professor of UCLA. He got his PhD from UC Berkeley, where his thesis title was Results on Martin's Conjecture. His research interest is on mathematical logic, especially recursion theory and descriptive set theory. So he will be giving the recursion theory portion with the course along with Junle Goh later this week. So without any further ado, I suppose I can pass it over to you, Patrick. You can go ahead.
Great, thanks. So yeah, I'm going to talk about recursion theory today. And since we have only a limited amount of time in the course, and there's also other stuff that Junle is going to talk about, I'll skip some details, but I'll try to give enough details to actually give a real sense of why things work. So I wanted to start with just some comments on what the historical motivation for computability theory, also known as recursion theory, is. And so I want to start by mentioning Hilbert's program. So the mathematician David Hilbert had this idea that maybe you could do the following in math. You could choose some kind of formal language and proof system, and then develop all known math within that formal system. Second, maybe you could then show that the system is consistent, so you could prove that that system will never prove contradictory statements. Then maybe you could show that that system is complete, so it actually will, every statement is either provable or disprovable in that system. And then finally, maybe you could actually come up with a sort of mechanical procedure for deciding which statements are provable. And if you could do that, you would sort of completely replace the human part of math in some way. You would have made it, you would have like completely solved the problem. For every mathematical statement, you could state it precisely and figure out whether it was true. The first step in this program was basically accomplished with the development of ZFC set theory and first order logic. So if you've been going to the, or if you go to the other courses, I think in this series, you'll see some of that. The second part, as I said, means that the system can't prove any contradictions. The third part means that it every statement is either provable or disprovable. And then this third part was sometimes called the Einstudungs problem or something like that. I'm not going to try to remember how to spell it. So that was Hilbert's program. And again, you can kind of think of this whole thing. The idea is supposed to be, you have this kind of machine, computer or something, although computers didn't exist at the time. And you write down any mathematical statement, like for instance, for all n greater than or equal to 3, for all a, b, c in the integers, if they're all non-zero, then a to the n plus b to the n is not equal to c to the n. So that's the statement of Fermat's last theorem. And you feed it into this machine, the machine chugs along for a while, and then eventually produces the result, which in this case is provable. And instead of waiting 300 years to find out if Fermat's last theorem is provable, you would just immediately know. So that was Hilbert's dream. Unfortunately, first Gödel showed that 2 and 3 in this program are impossible. And a little bit after that, Alan Turing showed that number 4 is also impossible. And that's really the origin of computability theory, is Turing's proof that number 4 is impossible. And the point of all this is to show that number 4 is impossible. What do you really need to do? You need to actually give a mathematically precise definition of mechanical procedure or computable or whatever so that you can actually prove things about it. Otherwise, this is just on the level of some sort of philosophical statement or something. So the beginning of computability theory was Turing's formal definition of computable so that he could actually prove that this is not possible. And then subsequently, people proved a lot of things about what's computable and what's not, and so on and so forth. So that's the origin of computability theory, which is also called recursion theory. Let's talk about what does a mechanical procedure mean? Well, what do we want from a formal mathematical definition of this? First, well, we want a mathematically precise definition that we can actually prove things about. Second, we want to know that definition actually corresponds to what we intuitively mean by computable. So we want some kind of maybe philosophical argument for why that definition is reasonable. Next, it's maybe reassuring if we can actually prove that a lot of functions which are intuitively computable are also computable according to our formal definition. And also, if we try to show that lots of such functions are formally computable, if we don't come up with any counterexamples, that's also reassuring. So if we don't find any functions which are intuitively computable but not according to this formal definition. And then finally, if there are multiple different approaches that all yield the same definition. That will reassure us that like this is kind of a very natural notion, and it wasn't just some quirk of the exact definition we used. And it turns out that, at least most people's opinion, all of these things have been achieved. So let me just mention number 4. Around the same time, a lot of different people gave definitions, formal definitions of computability. So Gödel defined something called the general recursive functions. Turing defined something which are now called Turing machines. He didn't call them that. There was lambda calculus, post-rewriting systems, and so on. And now in the modern day, of course, there's a million programming languages. And it turns out that all these things are equivalent. And furthermore, what was Turing's biggest contribution? So it actually turns out some of these things were defined before Turing defined Turing machines. But his great contribution, I would say, in this aspect at least, is, or at least one of his contributions was giving the most compelling philosophical justification that his definition was correct. Okay, so that's kind of a brief overview. So what am I going to try to talk about today? Actually, I'm going to skip this last part for now. So I'm going to try to formally define computable using actually Gödel's definition, which I said was this general recursive function definition. We're going to do that because that definition is easier to work with sometimes, easier to prove things about, requires less cumbersome notation and so on. Then I'm going to give you some examples to show that at least some intuitively computable functions are also computable according to Gödel's definition. In other words, they are general recursive functions. And then finally, I want to at least briefly describe Turing's definition and why he argued that it's a sort of correct definition of computable, and briefly mention how you can show it's equivalent to Gödel's definition. So that's basically the plan for today. And then maybe in the next session, I'll do this last item. So let me remove it for now. And as a final comment, in the modern day, I think many people have experience with programming languages. So many people have done a little bit of coding. And if you've done that, sometimes it feels like, why do we need to spend much time setting up a definition of formal computability and justifying that it's valid and so on? Because I don't know, if you've programmed a bit, you just feel like you know what it means for something to be computable. You know what it means to be able to write a Java program that does something, or a Python program or whatever. But at the time that Turing was working, this was not really obvious at all. So in 1930, computers did not exist. No programming language had ever been invented, really. Well, maybe, but not really. And so it really wasn't obvious at all to people what computable meant formally. So, David Hilbert had never seen a programming language or a computer or code or anything. Okay, so that's the setup. Now we're going to switch to some more sort of technical details. So this is kind of the overview. And by the way, feel free to let me know if you have questions or if I'm going too fast or too slowly or anything. Okay, so we're going to start, as I said, with defining Gödel's definition of computable. And that's actually going to take up most of the time. So in particular, what we're actually going to define is what it means for a function which takes natural numbers as inputs and gives you a natural number as output, what it means for that to be computable. And in case you think this is sort of too narrow, like why should we only allow natural numbers as input or output? It's easy to switch to other domains. For instance, infinite binary, the arbitrarily long binary sequences, arbitrarily long finite binary sequences, which you sometimes see denoted like this. So once you set up this definition, it's not that hard to change what the domain is. But just for the sake of concreteness, let's stick with this particular setting. So we're going to define computability of functions on the natural numbers to the natural numbers. And in Gödel's definition, it's actually convenient to first define a somewhat smaller class of functions, which turns out to be smaller than the class of computable functions. So everything in the class we're about to define is computable, but it doesn't cover all the computable functions. And this class is sometimes called the primitive recursive functions. I'm going to abbreviate it PR. And it's defined as the smallest class of functions from natural numbers to natural numbers, which contains 3 functions and is closed under 2 operations. So the 3 types of functions it contains is constant functions, the successor function, and projections. And now I'm going to say what each of those are. So the constant functions, these are functions that maybe I should say it like this. Here's one example of a constant function. It takes an input n, and it just always gives you the number 17. So this is the constant function with value 17. I'm going to sometimes denote that C17. Next, the successor function. This is just the function that takes a number and gives you that number plus 1. And finally, projections. These are functions that take multiple inputs. So they might take like 4 inputs, n1, n2, n3, and n4. And they just always give you the same one of those inputs. So maybe this projection function always gives you n3. So it takes 4 numbers and gives you the third of those numbers. And I'm going to note this p for 3 to denote it takes 4 inputs and gives you the third of them. So these are all like very simple functions, obviously computable. So they're all counted as primitive recursive. And then the set of primitive recursive functions is closed under these 2 operations. First, something sometimes called composition, or also sometimes called substitution. And then another operation called primitive recursion. And in case you're not sure what those terms mean, I'm going to define them in the next couple slides. And then more formally, you can define the set of primitive recursive functions as the intersection of all sets of functions which contain these ones on the left and are closed under the operations on the right. So if you want to prove that some class of functions contains all the primitive recursive functions, one thing you can do is show that it contains these functions on the left and is closed under the operations on the right. And essentially, intuitively, that's true of the computable functions. So that's why all primitive recursive functions are computable. So now I'm going to describe composition and primitive recursion. So composition, this is the principle. If you have a function f which takes little n inputs, and then functions g1 through gn, which each take k inputs, if they're all primitive recursive, then so is the following function. The function that takes k inputs and given k natural numbers, what output does it give you? It gives you f with f's first argument is g1 of n1 through nk, and so on. So first you apply all the functions little g to the input, and then you apply f to that. And sometimes I'm going to denote this as f composed with g1 through gn. So I'll use that notation. So let me just do a couple examples to clarify the notation. So suppose you have f is the projection onto the second coordinate. So remember, we had all projections, and g1 is the successor function, and g2 is the constant function with value 8. And I should say I'm going to denote successor sometimes as s. So let's see, what is h of f composed of g1, g2? Well, h of little n is going to be f of g1 of n, comma g2 of n. G1 of n, that's the successor, so that's going to be n plus 1. And G2 of n, that's always equal to 8. It's the constant function. And now f is projection onto the second coordinate, which means it just gives us the second of its inputs. So it's equal to 8. So in fact, here, h is also equal to C8. So we didn't get anything new by applying composition here. But that's what composition does. Now let's see a case where we do get something we didn't have before. Let's say f and g are both the successor function. So in this case, like little n would be 1, and little k would also be 1. Here, what is h of n? Well, it gives us f of g of n, which is f of n plus 1, and f gives us the successor of that, which is n plus 1 plus 1, in other words, n plus 2. And by induction, you could actually show for every n, the function m maps to m plus n is primitive recursive. So you just compose the successor function with itself n times, and you'll get this. So that's how composition and substitution work. Let me now describe primitive recursion. So this one kind of looks funny at first, I think, but the idea of it is not so complicated once you get past the notation. So in primitive recursion, you have two functions, little f and little g, and the first takes k inputs and the second takes k plus 2 inputs. And you get a function that takes k plus 1 inputs, and it has the property that when the first input is 0, it's just doing exactly what f does with the rest of the inputs. And for every other input, if the input is n plus 1, then g tells it what to do. And in telling it what to do, it uses the previous value of h. So h is the unique function that satisfies these two properties. The second property is for any n in the natural numbers. You can show by induction that h, there is a unique such h. And the primitive recursion says, if little f and little g are primitive recursive, then so is this function little h. And you should think this is some form of recursion because in defining one value of little h, we're using some other value of little h. So you can kind of think we're recursing, or we're making some recursive call to little h with n instead of n plus 1. Okay, and this is maybe easier to understand if you set k equal to 0 and just ignore all these extra inputs. Although sometimes we will use larger values of k. So if k equals 0, f is a function that takes no inputs, so it's actually just has to be a constant. So in that case, it's saying something like h of 0 is this constant a, let's say, and h of n plus 1 is equal to g of n comma h of n. So it's saying like at 0, you just get this constant, and at the next value, g tells you how to get that value from the previous value, and so on. So that's the idea of primitive recursion. And now let's do an example again with k equals 0. So with like no extra inputs. Although again, often you do want to have these extra inputs. So in the example, let's say the starting value is 7, and the function g is the successor function composed with projection onto the first coordinate. So first, let's try to figure out what g is doing. So remember, g should take two inputs, n and m, and it's going to give us the successor function of p21 of nm. And the success, well, p projection onto the first coordinate is just going to give us n. So the successor of this is going to just be, so this is just going to give us n plus 1. So in other words, sorry, I think that I made a typo here, and what I meant to say was projection onto the second coordinate. So if we change that, I think this will become a more interesting example. So projection in the second coordinate will give us m, and this will be m plus 1. So here, let's calculate what h is doing. H of 0 is just going to be a, which is 7. H of 1 is g of 1 comma h of 0, which is g of 1 comma 7. And what does g do? It takes the successor of the second coordinate. So this is going to be 8. What is h of 2? It's going to be g of 2 comma h of 1, or in other words, g of 2 comma 8. Again, g will take the successor of the second coordinate, so it will be 9. And you can continue like this and see in general, h of n is actually going to be n plus 7. Okay, so that's how primitive recursion works. We're going to do more examples, so hopefully it will become clear gradually how it works. So yeah, so let's see some examples. So now we're basically just going to verify that a bunch of different functions are indeed primitive recursive. So first, let's check that addition is primitive recursive. So the basic idea is that we want to define some function like h of nm equals n plus m. So how can we define this by primitive recursion? Well, first we're going to say h of n0 is equal to should be just equal to n, and h of n comma m plus 1 should be equal to well, n plus m plus 1. But if you put the parentheses in a different place, you see that we could really replace h of n plus m, or sorry, m plus m with h of n m. So in other words, this is sort of a recursive definition of addition. The n plus 0 is n, and n plus m plus 1 is n plus m plus 1. But now we need to fit this into the framework of primitive recursion. So we're going to apply primitive recursion to get this with k equal to 1. Our starting function f, well, it should be, I guess, ignoring this, this input. So maybe to fit into the way I literally defined things earlier, I want to switch the order of these two. So I want to say like 0n and something like this. I just had the order backwards from before. Okay, so little f should take one input n, and it should just give us n back. And you might be worried we don't actually have that function. That's the identity function. But we do have it because it's the projection of one input onto the first coordinate. So P11 of n just always gives us n. In other words, it's the identity function. And then what should our function little g be? So little g is supposed to take a number n and a value a, which you should think corresponds to h of nm. And then it takes this other argument, in this case, m. And what should it give us? Well, we want it to give us just a plus 1. Okay, so then you can check if we actually define things this way, we'll get a function h such that h of 0n is equal to f of n, which is equal to n, and h of n plus 1 comma m is equal to g of n comma h of n m comma m, which is h of nm plus 1. And by the way, why is it? Why can we do this? Well, this is the successor composed with projection onto the second coordinate. So if you worked out, for instance, some values of this, you'd see that like h of 1n is going to be h of 0n plus 1, which is just n plus 1. H of 2n is going to be h of 1n plus 1, which is n plus 1, another plus 1, so that's n plus 2. So you can then verify this really is addition. So that's how you can use primitive recursion to define addition. And since we were applying primitive recursion to functions we already know are primitive recursive, that tells us that addition is primitive recursive. Okay, so let me know if you have questions about this. Now let's do some more examples. I'm going to go slightly faster on these. Hopefully you've started to get the idea of how primitive recursion works. So let's show that multiplication is primitive recursive. Well, the idea is, let's say we want to define h of nm is equal to n times m. How can we do this? Well, first let's define h of 0m. So this is 0 times m. This should just be equal to 0. And now let's define n plus 1 times m. This should be equal to, what we want it to be equal to is n plus 1 times m, which is nm plus m. So what we should do is this nm is what h of nm is supposed to be. So you can just write h of nm plus m. Okay, and that's basically the entire proof that multiplication is primitive recursive. If you want to be more formal again, what you can say is, again, we're doing primitive recursion with k equals 1. Little f is the constantly 0 function. And little g takes n, a, and m and it just gives you a plus m. And how do we know that this function is primitive recursive? Well, that's what we just saw. Well, more or less what we just saw. So g is equal to the function that adds two numbers together, composed with projection onto the second coordinate and projection onto the third coordinate. So we basically want to add together two numbers, but we have to ignore the first number we're given. So that's why multiplication is primitive recursive. Let's do maybe one more example like this. So exponentiation is primitive recursive. So again, we want to define h of nm to be n to the m. So we can do this by setting h of 0m. This should be, well, now there's kind of a problem. This should be 0 to the m, so it should be 0. But then if we try to define h of n plus 1 m, we would want this to be n plus 1 to the m. And it's maybe not so easy to define that in terms of like n to the m. So instead, we're going to take a different approach, and we're going to define it in terms of recursion on this, on m instead of n. So in other words, h of n0, this should be n to the 0, which is just 1. Oops. And h of n plus 1, this should be n to the m plus 1, which is nm times n. So in other words, this should be h of nm times m, times n. So we have sort of given a definition in terms of primitive recursion, except that in primitive recursion, we were supposed to be doing recursion on the first input rather than the second. So what we should really define is h of nm equals m to the n, h of 0m equals 1, and h of n plus 1m equals h of nm times m. Which looks a little funny because, I don't know, the order of n and m are reversed from the way you would normally want to write it. It's just a quirk of the exact way we set up primitive recursion. But the question is maybe, so here, h of nm is actually equal to m to the n instead of n to the m. And what if we want the function that sends n comma m to n to the m instead, so in the right order? So is that also primitive recursive? It would be kind of troubling if it's not, because it's just a very simple modification of this one. So the answer is we can just define a function by h composed with two projections. First, the projection onto the second coordinate, and second, the projection onto the first coordinate. So this is the effect of swapping the input stage. So if we apply this to some inputs n and m, this is going to be h of p22 of nm and p21 of nm. So that's going to give us m comma n, which we have seen is equal to n to the m. Okay, so sorry, I think it gets a bit confusing with all these little n's and m's and so on. But the basic idea is, even though primitive recursion, we had to sort of be doing recursion on one of the first input in particular, it's easy to swap around inputs with these projection functions. So the primitive recursive functions are not super limited. Okay, and we'll do maybe one last example a little bit faster. So say we want to show that this particular polynomial in 3 variables is primitive recursive. How can we do that? Well, basically, we can just compose a bunch of functions that we've already seen are primitive recursive. So let's define F1. And I'm going to refer to mult as the multiplication function that we've already shown as primitive recursive. Oops, sorry. What I want to say is mult of projection onto the first coordinate together with projection onto the first coordinate. So our function is supposed to take 3 variables. The first one is x. So this f1 is going to be x squared. I'll say it again in a moment. We can define f2. We can try to get the function 2x. So to do that, we can take the composition of mult with the constant function 2 and p(3,1), and so on. We can just kind of build up different parts of this expression. Oops, sorry, I made another mistake. So this should be f2 and f3, because now we want to multiply together these 2 terms. Okay, and then we can add together this x squared term that we already have with this term. And then finally, we can add together all of that with the constant function 3. So just to verify this, f1 of xyz, we're going to projection onto the first coordinate 2 times and then multiply those 2 together. So this is going to be x times x, in other words, x squared, and so on. f2 of xyz, we take the constant function 2 and multiply it by projection of the first coordinate, so it's 2x. Here we take projection of the second and third coordinates and multiply them together, so we'll get yz, and so on. Okay, and we finally built up to the original polynomial. And in general, this is how you can show that things are primitive recursive, is you just keep building up more and more complicated functions. And to get the next most complicated one, you either use composition or primitive recursion. There's a lot more functions that you can show are primitive recursive. So here's some more examples. Every polynomial you can show is primitive recursive. Also, finite sums and products. So if f is a primitive recursive function, then so is the function that maps n to the sum of the first n values of f, as well as the function that maps n to the product of the first n values of f. So those functions are primitive recursive. The predecessor function, which subtracts 1 from a number unless the number is already 0 and does nothing. This truncated subtraction. So this is a function that tries to subtract m from n unless n is smaller than m, because then we would get a negative number that our codomain is supposed to be the natural numbers. So then it just gives you 0. So this is the function 0 if m is greater than n and n minus m otherwise. So here we're just dealing with a quirk of the fact that we chose to look at functions from natural numbers to natural numbers. You might more naturally want to define subtraction as a function onto the integers, but we just said for concreteness, we're only going to use natural numbers, so we can't do that. So you have to do some trick like this. And finally, the function checking if n is equal to 0. So let's say the function that's 1 if n equals 0 and 0 otherwise. So using just the kind of things we've done so far, you can check that all of these are in fact primitive recursive. If you really want to understand how to define things by primitive recursion, some of these are maybe good exercises to do. Next, there's something else I need to say, which is so far we've just been talking about what it means for a function from natural numbers to natural numbers to be primitive recursive. And later we're going to talk about what it means for such a function to be general recursive and so on. But what about a set of natural numbers? What if we want to say a set is computable? So we're going to define that just in terms of functions on natural numbers. So first, let's recall a definition. If A is a subset of natural numbers or some product of natural numbers times natural numbers or whatever, we'll define the characteristic function of A as the function it takes k inputs in the natural numbers, and it gives you 0 if those k inputs are not an element of A. And 1 if they are an element of A. So it just tells you whether the input it's given is an element of A or not. That's the characteristic function of a set. And we'll say that a set is primitive recursive if its characteristic function is primitive recursive. Okay, so that's what I mean by saying a set is primitive recursive, even though I said I would only talk about functions. And so let's see some examples of this. What kind of sets are primitive recursive, or at least a few? So first, the set that just contains 0 is primitive recursive. That's because its indicator function is just this is 0 function that I mentioned before. So if you do that exercise, you'll show that is 0 is primitive recursive, which will show that this set is primitive recursive. In fact, for any natural number n, the set that just contains n is also primitive recursive. That's because you can define it as the is 0 function composed. Well, I need to maybe give this an input. Composed with truncated subtraction of n minus m plus truncated subtraction of m minus n. So if n is not equal to m, then at least one of those will be a positive number. So their sum will be a positive number. So the whole thing will not be equal to 0. The equality predicate is also primitive recursive. So this is formally the set n comma n such that n is a natural number. And this is, of course, a subset of natural numbers squared. So that one, the proof is almost identical. its indicator function is simply is 0 of n minus m plus m minus n. And the difference is before here, this n was really you'd have to use the constant function with value n. And here you're using the input. Similarly, the less than or equal to and greater than or equal to function, sets are primitive recursive. So less than or equal to, this is the set of n comma m in n squared such that n is less than or equal to m. And I guess you can imagine what greater than or equal to set is. And the indicator function of this, this is equal to is 0 of, in this case, it's just n minus truncated subtraction m. Because if n is larger than m, then that truncated subtraction will be positive. Okay, and the greater than or equal to is very similar. So one way you could define this actually is as the less than or equal to function composed with these two projections that swap the inputs. You could also define it directly. Okay, so if you believe that all these previous functions were primitive recursive, then all of these ones also are. And now here's maybe a couple lemmas that tell you other sorts of functions you can define using primitive recursion. So suppose little f and little g are both primitive recursive and big A is a primitive recursive set. Then you can define a function using definition by cases on whether the input is an element of A. So then the function from n to the k to n defined by, it sends the input n1 through nk. It uses f if the input is an element of A. It uses g otherwise. So defining a function this way is usually called definition by cases. And as long as the set and the functions you start out with are primitive recursive, this is also always primitive recursive. I guess there's a few ways to do this, but one would be to note that this function is equal to the indicator function of A multiplied by the function f plus 1 minus the indicator function of A multiplied by g. So the indicator 1 minus the indicator function is 0 if the input is an element of A, and 1 if it's not an element of A. So you can then verify that this function is the function we want. So when you're defining things by primitive, if you're trying to show that something is primitive recursive, then you're justified in using definition by cases. Let's do another similar example to this. This is something called bounded quantification. So if A is a primitive recursive function, if A is a primitive recursive set, then so are the two sets. I'm going to call the first one, there exists x less than or equal to n applied to A. This is the set of n comma m1 through mk such that there exists some x less than or equal to n, so that x comma m1 through mk is an element of A. And similarly, bounded quantification with a universal quantifier. So these are both primitive recursive sets. These are both also subsets of n to the k plus 1. And again, this is called bounded quantification. And the proof is basically, for the first one, its indicator function one way you can write it is as this. So if there doesn't exist such a little x, then that sum will just be 0. And if there does exist such an x, then the sum will be non-zero. And when you take 1 minus it, you'll get the right thing. And you can do something very similar for universal quantifiers. So yeah, I mean, this is the kind of thing maybe where it's easier to just work out on your own why this works than it is to hear somebody explain it. In any case, the point of all this is that we can build up a lot of functions that are primitive recursive. We can build up a lot of tools for building up more functions. So primitive recursive functions actually have a lot of closure properties. I want to maybe not do more examples of that, but mention some other perspectives about primitive recursive functions. And then maybe we'll take a little break and then we can move on to actually defining computable functions. So one perspective is that another way to define primitive recursive functions is to specify some programming language with a restricted set of operations. So this is a programming language where what can you do? You can set a variable equal to some constant. So here x is a variable and c is some actual natural number. You can increment any variable, so you can add 1 to it. You can have like if then else structures, and the things you're allowed to put in the if statement are things like x equals y, x is less than y, x is greater than y, and you're also allowed to combine them with ands and ors and nots. And finally, you're allowed to have for loops. So if x is a variable, you can loop from I equals 1 to x and do something in the body of the loop. So if you have a programming language with basically this instruction set, then the programs you can compute in that programming language are pretty much exactly the primitive recursive functions. And you should think this for loop corresponds to primitive recursion. So in primitive recursion, recall, if you want to know what is the value of like h of n plus h of n, well, you can figure out h of n in terms of h of n minus 1, which you can figure out in terms of h of n minus 2, and so on. So that corresponds to some kind of for loop where you build up from h of 0, h of 1, h of 2, all the way through h of n, but you only need to do n steps. You don't need to do like some much larger number of steps to figure out h of n. So basically, one way to think of primitive recursion is that it corresponds to for loops. And what makes this programming language weaker than other programming languages is it sort of only has for loops and no while loops. So if you're not familiar with programming, you can maybe ignore this perspective, and the other definition we gave is perfectly valid. But this is maybe a useful way to think about it. And there is even like a formal version of this. So for instance, there's something called the loop programming language, which is exactly like this. You can look it up if you want to. Okay, so let me now discuss one last thing, and then maybe we can take a short break. So I kind of already said the answer to this, but one could ask, is every computable function primitive recursive? So there's some intuitive argument that every primitive recursive function is computable, but is it true the other way around? And actually, it turns out the answer is no. And this was first proved by some guy named Wilhelm Ackermann. And this was actually proved before anyone gave a definition of computable function. So at the time, maybe it wasn't obvious at first whether or not primitive recursive meant computable. And the key idea of the proof is basically that primitive recursive functions cannot grow too fast. So there's some, if f is primitive recursive, there's some limit on how big f of n can be in terms of n. But general computable functions can be larger. That's sort of the idea of the proof. That's a bit vague. So I want to maybe give some indication of how the proof works, but not actually give a complete proof. So one way to describe it is in terms of this thing called Knuth up arrow notation, which is some way of describing large numbers, basically. So n up arrow m, this means n to the m. So one up arrow is exponentiation. And each additional up arrow you add, you like repeat the previous operation m times. So n up arrow m means you take n to the n, and then you take that to the n. Well, should really be putting the n's down below, but anyways, you have a tower of exponents of length m. So you iterate exponentiation m times. And so on. So in particular, if you have n plus 1 up arrows, what does that mean? That means you start with n, the argument on the left, or sorry, now I'm calling it a apparently, the argument on the left, and you write n up arrows. And you apply that, maybe let me describe it sort of the other way around. So you start with a, and you put n up arrows with a, or I should say b up arrows with a, sorry. And then you take that and you do it again with n up arrows. Oops, sorry, I've made two typos now. So let me restart. So what does it mean to do a n plus 1 up arrows b? It means you start with a and do n up arrows of a. And then you repeat that again. So you do n more up arrows with a. And then you keep repeating that. And the number of times you repeat it is b. So each time you do some set of up arrows, you're doing n of them. So as I said, you start with exponentiation. The next level is like you iterate exponentiation m times. The next level is you iterate that m times. So this is some sequence of very fast growing functions. And it turns out that like every primitive recursive function is bounded by one of these. So if we consider the function set of functions f from n to the k to n, such that for some n, f is eventually always less than or equal to it's eventually bounded by n1 plus n2 plus so on, and then n up arrows of again n1 plus n2 plus so on. It turns out that set of functions is closed under the primitive recursive operations, and hence it contains all the primitive recursive functions. So functions whose growth rate is bounded by some number of Knuth up arrows, those functions are all contain all the primitive recursive functions. So this is what I mean when I said the primitive recursive functions can't grow that fast. They can't grow faster than some finite number of up arrows. But the function which takes n as input and gives you as output n with n up arrows n. So this grows faster than any finite number of up arrows. And if you believe what I've said, that means it's not primitive recursive, but it is computable. I've kind of actually just described to you how you could compute it with my definition of the up arrow notation. So the whole idea of the proof basically is to find some set of functions and show that every primitive recursive function is bounded by one of those functions, and then construct a computable function that grows faster than all of them. So that's the idea of the proof. Now we'll talk about how to expand the definition of primitive recursive to actually capture all the computable functions. But maybe first we can take like a 5-minute break or something, because I think this is quite a long time to listen. So maybe I'll start speaking again in 5 minutes. But in those 5 minutes, feel free to let me know if you have questions or anything.
Okay, thanks, Patrick. So 5 minutes break. Yeah, just chime in if you have any questions. I will keep an eye on the chat for you.